What are stress singularities in FEA stress analysis? Imagine trying to measure the highest stress in a structure and getting a number that just keeps climbing without stopping. That's what stress singularities are in finite element analysis. They happen at specific points in a model where the calculated stress becomes infinitely large. This isn't because the material actually reaches infinite stress, but because of how the model is set up or the shape of the object. Stress is first divided by area, so when the area approaches zero, the stress calculation shoots up. Think of sharp corners or points where loads are applied at just one spot. These are common places where singularities occur. They are different from stress concentrations, which are high but finite stresses around features like holes or fillets. Stress concentrations stay within a limit when the mesh gets finer. But singularities keep growing as the mesh refines, never settling on a specific value. Usually, causes include sharp inside corners, point loads or supports at a single node, sudden changes in boundary conditions, or contact points with sharp edges. These singularities are local effects, meaning they don't ruin the entire analysis. According to St. Venant's principle, the influence of these local effects diminishes quickly with distance. So, stresses away from the singularity are still reliable. When analyzing results, it's important to interpret these infinite stresses correctly. They are not physically real but are artifacts of the mathematical model and idealizations. If the singularity is outside the critical area, it can often be ignored. But if it's in a key part of the design, there are ways to handle it. For example, refining the mesh carefully can help, but remember that stress at the singularity will increase. Changing the geometry by adding fillets or rounding sharp corners can reduce the effect. Applying loads more realistically, spreading forces over an area instead of a single point, helps avoid singularities. Using advanced modeling techniques like elastic supports or contact modeling instead of fixed constraints can also make a difference. When the singularity occurs at a crack tip, fracture mechanics methods are used instead, focusing on stress intensity factors rather than raw stresses. To sum up, stress singularities are mathematical artifacts caused by idealized shapes and loading conditions. Recognizing and managing them is key for accurate stress analysis and safe mechanical design. Understanding where they come from and how they behave helps engineers interpret finite element analysis results correctly and make better design choices.